So I'm going to give an overview of the instrument and the science cases that have driven this design. So I'm currently based in Granada at the Institute of Astrophysics of Andalucía in Spain. So let me start. So this instrument has come along in the environment of looking for something to cover the scientific needs of the 2020s in Gemini. So there's going to be very prominent new facilities coming along in the next years, like LSST. Well, ALMA is already there. SKA will be coming. The different ELTs, the James Webb is going to be soon launched, and this is going to change a bit of the paradigm of the role of these 8-meter telescopes. So Gemini, thinking ahead, thought of having some way to find a niche in that environment, and their idea was to get a new workhorse instrument that would cover many science cases, and in particular they wanted something that was very broad wavelength, covering visible and near infrared, and that would take into account the very strongly coming time domain astrophysics. For this, we would be using the experience of old instruments to take the things a little bit a step further. One of the main and most relevant instruments that are going to be driving this instrument is the Large Synoptic Survey Telescope. As most of you probably already know, this is an 8-meter class telescope that's very peculiar. It has a huge field of view and an enormous camera with more than 3 gigapixels. And during 10 years of survey, it's going to observe a ridiculous amount of sources. It's going to be detecting millions of new transient sources that it's going to be generating alerts in almost real time, which are going to need to be properly characterized and followed. Of course, we're not going to follow all of them from here, so a selection is going to have to be made, and those data are going to be those most interesting sources are going to be studied by an instrument, for example, like OCTOCAM. So there will be a strong synergy. Especially, we're going to mount this on a telescope that is on the same mountain as LSST. So the synergy is going to be very, very strong. So the history of this, of how this instrument came to be in Gemini, starts in 2014. Well, it starts probably much earlier, but in 2014, a call for feasibility studies for this future instrument was issued by Gemini. This was in late 2014. We already had some kind of idea of an instrument that we wanted to do, and it fitted very nicely to what Gemini seemed to be looking for. So OCTOCAM was one of the 4 projects that was selected in this call, and during the following year we performed a feasibility study. All the 4 feasibility studies were delivered and presented here at HILO in October 2015. So after this was evaluated. It was not a competitive thing, so we're just evaluating ideas and thinking of what could be useful for Gemini. And in 2016, in August, they issued a call for an instrument design, where they got some of the characteristics of different instruments that were presented there. They figured out what they thought could be done and put it into our call, to which we responded with a slightly modified version of what we had presented the year before. And well, luckily, at the end of last year, we were called that we had been selected, and after a process of negotiation and contract, we managed to sign a contract to deliver this instrument, hopefully by the beginning of 2022. So it should be there before LSST comes online. So let me show you a bit of the team that is making this instrument possible. So there are 4 nodes in the collaboration. So Cristina Truene and I are in Granada in Spain. So I'm the principal investigator. Cristina is the deputy project manager. She's taking care of the management of the things being done in Spain. The main contractor of this project is the Southwest Research Institute in San Antonio, in Texas. That team is being led by Pete Roming, who is co-PI and the main project manager of the project. Susan Paul is doing the systems engineering together with Tonya Brody, and well, they have a lot of experience in space missions. So ground-based is a bit of new for them. but they have a huge experience in the systems engineering part. So it's been kind of downscaling a little bit, but it's great to have all that experience together. So Ronnie Kilo is taking care of the work package. He's the lead of the work package in software. Amanda Bailey is doing the detectors, which is an extremely relevant part of this project that you'll see. We have a lot of detectors there, both optical and infrared. Kelly Schmidt is doing the cooling of part of the detectors, and Christian Persson is the lead of electronics, the electronics of the instrument. On the other side, within Spain, we are getting the optomechanical design done by Fractal. Fractal is a private company specialized in ground-based instrumentation. They just finished commissioning the Megara instrument for the GDC telescope, the 10-meter GDC telescope, very successfully, which I think they just finished last week. So Marisa is the contract manager, and Ernesto Sánchez Blanco is doing the optical design, and Manuel Maldonado is doing the mechanical and the thermal part of the instrument. Finally, we have Alexander van der Horst, who is the project scientist. He's based in the George Washington University in Washington, D.C. And he's taking care of putting together the science team and getting all the input from the science team. And you'll see now that he's doing a huge job to put that together and get a very good representation of the Gemini community. Also in the George Washington University, we're going to have the development of the pipeline. We don't have the picture here yet because that's not been started yet. There's only been some definitions made of that, but the work has not started in the development. Probably at the end of next year, we'll begin to have this person already identified. So as for the science team, we've put together a pretty large science team. So we have over 50 people that cover the full Gemini community. I mean, all the Gemini countries included there. There's some external science members where we felt that we could get some input from other communities also because there was an important expertise. And we're getting a lot of information from them. We now and then we do surveys among this team, and we try to fine-tune together with them the characteristics of the instrument. The science topics that are covered by this team, you can imagine that it's very broad. You have 50 people from all sorts of science backgrounds. So you can see that not only transients that we were talking about before, but from the solar system to the most distant universe is covered within the science cases that are interested in using OCTOCAM and that think that OCTOCAM might be a breakthrough instrument for their science. However, among these science topics, we have to select those that are going to be driving the design of the instrument. So if there's some kind of a priority that needs to be taken, because you cannot always satisfy everybody, we are prioritizing what we call the science drivers, which are what I said before, the rapid characterization of transients, the follow-up of LSST, and then the physical understanding of extreme phenomena such as gamma ray bursts, supernova, magnetar, tidal disruption events, some very extreme phenomena. We also have a strong commitment with the solar system, astroseismology, and then we go to the very edge of the universe, studying the first generation of stars, their environments, and the evolution of galaxies. So I'm going to go very rapidly through some of these science topics. I start with gamma ray bursts. I'm a little bit biased there because that's where I've done most of my science. So to me, OCTOCAM is going to be one of the most revolutionary instruments for gamma ray bursts because it's going to be able to do things that have not been available until now. It's going to be one of the instruments better prepared to detect the furthermost gamma ray bursts and study the environment of the galaxies in which they are produced. The multiband imaging and spectroscopy is very important for the modeling of these sources to study the emission, the interaction with the environment, the jet physics, and all these high time capabilities that I'll show you now are also very important for this kind of events, especially if you can react very quickly with the telescope, which is a capability that we're exploring. Of course, supernovae are a very important branch of astrophysics. And there are many things that OCTOCAM will do very well, like very fast response to supernova discoveries to try to do flash spectroscopy. The sensitivity and broad wavelength coverage, and I think are quite well adapted. Spectral resolution will be also very important to do late-time spectroscopy of supernovae, to study the mass loss and the progenitor through the emission and the environment. Through the infrared capability of the instrument, we can also study very well the dust that's being generated in these supernova explosions. And we can also try to push the limit of the Hubble diagram by observing type 1a supernovae in the infrared, and also exploring the possibilities. That's part of science being very interested in exploring the use of supernova type 2 as standard candles. Magnetars are also sort of objects of my interest. They're mainly in the galactic plane. They are neutron stars with very strong magnetic fields, with periods of a few seconds, between 2 and 10 seconds. So we're going to be able to use an instrument like this one, where you can do simultaneous observations, and you can do high time resolution observations to study the periodicity of this kind of objects, and compare it at the same time with high energy observations, where the periodicity is very easily constrained. So we can obtain very high time resolution observations folded together with the periodicity that we see in the X-rays, and observe it simultaneously in many bands, which is going to be something that's not so easy to do. And we expect to be able to do spectral studies that have basically not been done almost ever on this kind of objects. Another thing that is very in fashion now is the study of tidal disruption events. And there's many things, or very little, that I can say about these ones, because they are so varied in the handful of objects that have been studied to be tidal disruption events. There's a lot of different characteristics that have been observed. So having an instrument with such a broad wavelength coverage, and the possibility also to do resolve time studies, both in imaging and spectroscopy, can bring us a lot more detail and insight into this kind of still not fully understood sources. Extrasolar planets are a bit further away from my knowledge, but from our science team, we know that OCTOCAM might play an important role thanks to the high time resolution observations that we can do during transits, and the broadband simultaneous coverage in the different bands. We're going to be able to explore through photometry and spectroscopy, study the planets, and perhaps even the characterization of their atmospheres. That's going to be really exciting also work that we hope to be able to do. So with this, I'm going to move on and explain you a little bit of the concept of OCTOCAM. So the most important thing about OCTOCAM is simultaneity. So with a single instrument, you can try to improve the efficiency of the instrument. So you can have an imager that has a 50% efficiency. You can try to push that to 80%. You can try to push it a bit further, but then you begin to reach a hard limit. So the way in which you try to get more efficiency is through simultaneously observing in different bands. So what we're doing in OCTOCAM is building a multi-channel instrument, and there you can see where the OCTOCAM comes from. We're using 8 different channels. So in practice, we will be imaging in 8 different bands. So in some of the cases, this would mean something like multiplying the telescope into 8 different telescopes observing simultaneously the same field in some way. We also have a pretty broad wavelength range. So we're going from 3,700 angstroms all the way to K-band to 23,500 angstroms. And of course, this is nothing completely new. So we try to inherit experience from other instruments and other observatories. So we're trying to copy things that have been done well elsewhere and trying to push it a bit further. So we're inheriting the experience that has been gotten with Gronda, the 2.2 in La Silla, for doing multiband imaging. We are wanting to do spectroscopy in a similar, very broad wavelength range like X-shooter does at the VLT. And we also want to go for high time resolution like OCTOCAM, like UltraCam has been doing over the last decade. And we're putting all that together to build a completely new concept that is covering a region of the temporal resolution, spectral coverage, and spectral resolution diagram that's not covered by any other instrument in the world currently. So how do we do this? As I said, we have 8 independent channels, and we are feeding the different channels by the use of high-efficiency dichroics. So the dichroics let pass part of the light will reflect other different wavelengths. So we're splitting wavelengths. This is very efficient. We can transmit and reflect with efficiencies of higher than 97%. So we're losing very little light. One important thing of this instrument is, if you see here, we have the light coming from the telescope. This is the entrance window. We have an atmospheric dispersion corrector, which I'll explain later, which is an important part of the instrument. And we have a single focal station where we have the different slits, and which can carry also different elements, of which I will speak afterwards. After that, we have the different dichroics splitting the light into the different arms. And schematically, I'm just saying this schematically because you'll see that it's a bit more complex afterwards. We are having a very simple instrument. It's just a collimator, a filter algorithm, and a camera. So it's an imaging spectrograph, classical imaging spectrograph, just that we're multiplying by 8. Of course, the slit and the infrared part has to go inside a cryostat in order to constrain the thermal emission. So that's cooled. And we have a second window in the cryostat through which the optical light comes out to a warm, visible bench where we have all the optical arms. So that's the basic scene. 2 parts, one cold, one warm. As I point out here, I'll explain later, although it's not part of the baseline design right now, we're leaving some space in the focal station, taking advantage that we have a common focal station to introduce perhaps an additional element that could be an integral field unit or a spectral polarimeter. That's something that could happen in the future. It's not part of the baseline design, as I say. So what are the observing modes of this instrument? As you'll see, this is pretty simple in that respect. It's complex in the sense that we are multiplexing a lot the actual instrument itself in different components, in different cameras, but the instrument itself is very simple. So we have imaging and we have spectroscopy. So the standard imaging, it's a field of view of 180 by 180 arc seconds. We will offer the possibility to have actually a circular aperture if that's desired by the size case, where we have a field of view of a bit more than 4 arc minutes diameter. And we can also go in window mode. This is used for high time resolution observations. We can have multiple windows. Actually, the architecture of our detectors allows us to do symmetric windows quite easily. You'll see later that we have the optical detectors divided into 4 quadrants, so we can do 4 symmetric windows at basically the same price of doing 1. And we can, of course, do standard binning of 1 by 1, but we can also do other kinds of binning if the science justifies it. As for the spectroscopic part, we have a long slit of 180 arc seconds, so that's a quite long slit if you compare it with instrument with similar spectral coverage, and of course that disperses the light into each of the 8 different wavelength ranges that are adjacent to cover the full spectral range. We can also go for windowed spectral coverage in order to be able to go at higher time resolutions. The detectors we have 2 different technologies. We have E2V 4K by 4K frame transfer detectors in the optical, and you'll see that this is important. And we have the Hawaii 2RG detectors for the infrared bands. You see that here, this is the active area of the detector, whereas these gray parts are the frame transfer parts of the detector. These detectors have 4 readouts, so it can go 4 times faster than what one of those readouts alone would allow. And we're just illuminating the central part for the imaging of the detector, but we're using the full 4,000 pixels in order to get higher spectral resolution. As for, well, the good thing about these detectors is that you can expose, transfer the charge, which takes 60 milliseconds to transfer to the covered area, and expose again while you're reading out the next exposure. This means that in practice, if you're going above a certain threshold of exposure time, your dead time between exposures is 60 milliseconds. So that can be very useful to make the instrument efficient at the observatory. In the infrared, the arrangement is similar, but of course you have a CMOS detector. You don't have the capacity or probably the need of doing the frame transfer. These are much faster detectors. And again, we are spreading the spectroscopy further than what we're doing with the imaging. I go a little bit more in the imaging details. The imaging is basically constrained to a set of standard bands. So we're doing slow bands and the standard infrared bands. So it's GRI, Z, J, AY, J, it's K, S. So it's K short to avoid a bit of the extreme thermal emission. And as I said, we're using that technology of detectors, and we have very little overheads. So that's the coverage, the different curves of the filters. This is a plot of the limiting magnitudes that we expect to be achieving at 1 second and the half-an-hour exposure. So the field of view, you can see that it's not huge if you compare with other instruments. We have a 3x3 arc-mated field of view. If you compare with GMOS or you compare with Flamingos too, we have a significantly smaller field of view. But you have to take into account that we have 8 detectors simultaneously. So this means that if what your science requires is to do observations in different filters, we actually have an effective field of view of 72 square arc minutes, so much bigger than any of the 2 other instruments. Of course, we are observing the same field at the same time. If you use the 4.2 diameter field of view, the coverage is even larger. We're having over 100 square arc minutes of effective coverage. So if you want to do a survey in multicolor, this is probably going to be your instrument. As for spectroscopy, I'm going to try to show you why we're selecting this spectral range. This is the efficiency of the atmosphere as for bringing light down to the observatory. So you can see that it can reach down to 3,000 angstroms. You have the atmospheric bands that don't allow to get much light. That's between J band and H band, this window, and that's that band, and the other band between H and K band. This instead is the efficiency of 3 reflections in the Gemini mirrors. As most of you might know, maybe someone doesn't know, Gemini is quite unique in the coding of the mirrors. So instead of using the more classical aluminum coverage, Gemini is using a coding based on silver, which is extremely efficient for the infrared, and actually is much better than aluminum, all the way down to around 4,000 angstroms. The problem is that below 4,000 angstroms, it drops very, very sharply. This is a trait that was decided by Gemini, which I actually agree on. And if you combine this together with the... Okay, this doesn't work. I'm sorry, this got stuck. I think I lost connection. This short break, we continue. So we were with the efficiency of the mirror. When you combine those two, we end up having an efficiency coming into the instrument of around 25% above 3,700, but it becomes very, very low below. So we decided that was the point we wanted to cut. There's also some scientific reasons for trying to push it down to 3,700. So those that are doing a study of galaxies would be very interested probably in looking at the O2 line, well, not only galaxies, at O2 lines, the doublet at 3727 and 3729, a redshift 0, that will be covered by the instrument. On the other end, we can cover also a very interesting line at H alpha at a redshift of 2.5. So that's a pretty broad range. Also, the infrared coverage allows us to study the very extinguished sources. And as for spectroscopy, we're using volume phase holographic gratings, which are very efficient, especially if you have a sort of narrow wavelength coverage. And as we have quite constrained bands, they can be pretty efficient. The resolution that we're looking at is between 3,500 and 4,000 500 with the narrow slit, with the reference 3-pixel slit. This is important, especially in the infrared, where you need a resolution beyond 3000 if you want to look between the OH bands, if you want to resolve those OH bands to be able to look at the continuum of very faint sources. It's also nice to be able to have a bit more resolution to be able to study velocity field in galaxies. And you have to also have a compromise of not going too high, because then you're going to be losing those faint, the continuum of those faint sources. So we thought that that was kind of a sweet spot where we could work with OCTOCAM. Again, that's the estimated magnitude limits for a very short exposure of 10 seconds and a long exposure of 1 hour. Those are the different efficiencies. Don't look at the top one because we're not considering the IP right now. But the typical resolution, you see that it's at around 4000, a little bit above in the infrared, and a bit above in the optical, except for the bluest band where we have a bit lower resolution. This also, although we lose a bit of resolution in the blue part, that helps also because as you have a bit less resolution, you also have to compensate that decay in the efficiency at the very blue end. So you can compensate a bit that with that. Another thing is that we have an atmospheric dispersion corrector that works in the full range. This is what it looks like. So as you probably know, the atmospheric dispersion corrector, what it does is try to correct for that dispersion that you have in the light just by the effect of the atmosphere when you go down in elevation. It's quite demanding to do such a device that covers all the wavelength range. So it turns out not to be extremely efficient, as I'll show you in a minute, but we can make it work down to elevations of 40 degrees or 50 degrees zenith distance, which is quite good. And we have a loss of efficiency though of around 10%. That's the efficiency curve. So what does this mean? We're going to be able with this to use the slit in any angle. So the problem about this dispersion is that if you just put the slit for such a broad wavelength coverage as we have in OCTOCAM, if you put it in any angle, you're going to be losing the light from the extreme bands. So with this atmospheric dispersion corrector, we make sure that all the light is falling into the slit. However, in modes like imaging, you don't really care that much about that dispersion because you're just having one band, and the stars might appear a bit elongated when you have a very broad wavelength coverage, but as we have in single band, you will just have an offset and you still have point-like stars. So you will probably want to observe without. In other cases where you're observing a point-like source, like transient gamma ray burst or supernova, sometimes you're interested in having the angle to connect with the host galaxy, but sometimes you're just happy with having the slit in the parallactic angle, so the dispersion of the atmosphere falls along the slit. You're going to have some curvature in your spectrum, but you're going to have all the light in. So you could also work without the ADC. So what we've decided, and that's been decided recently, is to make this ADC retractable. Then you boost the efficiency by 10%, and you have less thermal emission in the infrared, and you're going to have a bit more efficient instrument. So that's going to be up to the observer to decide how he wants to do it. This is the instrument efficiency. Here you have the curve. These lines here that you see, the dotted lines, are what we are expected to do by the requirements of the contract that we have with Gemini, and you can see that we are doing quite well. So that red line is supposed to be the average of these high points, and the same for the blue ones. The blue ones are clearly above, and the red ones are also all above the limit that we have. You can also compare this with the telescope. Of course, when you put the telescope, the efficiency goes a bit down also. And but if you take the ADC out, you can see how you're boosting the efficiency. So for imaging, you can take it out and be a bit more efficient. And this is the OCTOCAM instrument without the ADC. We've begun to build exposure time calculators, signal-to-noise radio calculators, to understand better how the instrument performs You can see here how the limiting magnitude evolves with exposure time for a 5 sigma limiting magnitude with time. And here we have the expected limiting magnitude for a 1 second exposure when you want to go to high time resolution, or for a deeper imaging exposure. And the same for spectroscopy. In spectroscopy, we consider pixel by pixel, and we can calculate the signal to noise ratio. This is an example of a typical gamma ray burst spectrum with a slope of spectral slope of 0.6 and typical conditions of a seeing of 0.8 and an exposure time of 3,600 seconds. That's 1 hour of exposure for a magnitude that's 23rd magnitude in the G band, which I think turns out to be 22nd magnitude AB in the K band. So you can see the efficiency for that kind of spectrum is quite uniform. As for the mechanical design, you can have an idea here of what it's going to look like. That's the instrument support structure of Gemini, to which we hold. As you know, this is at the base of the telescope. The mirror will be above. The light is sent down through this hole, and there's a mirror that distributes the light either to OCTOCAM or to another instrument here, to the different instruments. So the design guidelines of OCTOCAM was to have an efficient instrument. So we want to maximize efficiency. We have a dedicated telescope. We want to use all those very expensive photons that are arriving to our instrument. We want to make it simple, and that's a relative meaning, because of course we are complex, having 8 arms in the same instrument, but we are simple. We have limited amount of moving parts. We have kind of shared optics. We have just one single mechanical structure to which all the cameras, all the arms are held. So we're trying to make that as simple as possible. It has to be compact because it has to be in the Cassegrain cage of Gemini. It has to be lightweight, relatively. This is a 1.5 ton instrument. We have a limit of 2 tons. And we want to make it, as I said, with the minimum amount of moving parts. If you have a lot of moving parts, that's just the possibilities of having problems in the future. We're using high efficiency dichroics, and the same for the volume phase holographic ratings. We try to keep the pupil constrained, the size of the pupil. That means also the size of the grisms. The grisms are not very big. They are like 60 centimeters, like 60 millimeters on the side. And we do have a single long slit, single focal plane, as I already said before. And in some cases, part of the optics are shared by different arms. That helps us to keep the thing compact and have to have less optical elements. Here is what the instrument looks like if you take it off the cage and you open this vacuum chamber. That's the vacuum chamber. That's the optical arm, the infrared arms up here, and the optical ones down here with a common optical bench structure. So that's in the cryogenic chamber. You see here, that's the ADC. Light arrives to this is the focal plane unit. First dichroic that divides the infrared light and the optical light that goes to the other side. And the collimator, out of the collimator optics, they are parts shared by the different arms. It's continuously split by different dichroics. And then here at the end, you find the 4 infrared detectors. The red things are the grisms. They move by pairs, so we don't have 8 motors to move the the grisms, but we have 4, and that helps simplify the complexity of the instrument. This is the focal plane unit. We have an aperture for the imaging. We have a slit area here with different slits. We have at least 5 different slits and a mask to select that one. And we're leaving an extra space for an IFU, spectral polarimeter, or whatever anyone can envision in the future. The schedule for the project, as I said, we want to be on the telescope commissioned in the spring of 2022. So it's a pretty tight schedule for those that have been involved in instrumentation programs. I think this is a quite tight schedule for such an instrument. We have just passed the conceptual design phase. We now are entering the preliminary design phase that will be finished in spring next year. Another year will be used for the critical design, and then we'll start building the instrument during these 2 years. After that, we'll have the the packaging of the instrument, all the testing will go to the telescope. We'll do the commissioning of the instrument, and hopefully it will be accepted and passed along to the observatory around that date, hopefully on time. So as possible upgrades, and I'm just going to mention this again, this is not part of the baseline design, but maybe if someone is interested in using this instrument in the future to propose other upgrades, you can start thinking about things. As I said, in the focal plane, we have an additional space that can be used. One of the ideas, and this was presented in the feasibility study and was not pursued afterwards, but it was quite quite decently designed by the time of the feasibility study. It's an integral field unit with an area of around 10 arc seconds by 7 arc seconds with resolution elements of 0.4 arc seconds. This has the full wavelength coverage and has the full spectral resolution, actually a bit more than the slit because we have a narrower slit, slitlets in each of the spaxels that we're gonna get. This was very interesting at the time. It was very interesting for the people that were doing gamma ray burst and supernovae host galaxies, so to study the environment in which they are produced. Also the massive stellar environments, also the TNO, the transnewtonian objects and comets were interested in using this kind of unit. We also thought about an adaptive optics IFU. As you know, Gemini can provide an adaptive optic beam, which could actually be used by this instrument by including an adaptive optics unit that would be adapted for this. So it would get the adaptive optics light and re-image it on the slit, producing an integral field unit of around 3 arc second at the site. This would work in principle for the wavelength coverage where the AO is efficient. So basically for the infrared. Okay. That's what the IFU would look like. It's 17 slitlets of 0.4 arc seconds. Another unit that we thought about was having a spectral polarimeter. This was based on the design by Franz Nick that they did for X-Shooter, which was not implemented in X-Shooter either. And it's quite an exciting idea. You just don't try to do all the correction of the polarizer in wavelength, but on the other hand, you know very well how the modulator is polarizing the light. So by observing several angles, you can reconstruct the polarization of the light in the full spectral range. So you will have the target aperture and you will have two sky apertures to compare. You would do several observations with different angles and you will get the polarization. Another very interesting idea that Franz had was to do this with a much higher frequency modulator that would allow you to get the polarization of a source in a single exposure. You would be paying the price of spectral resolution because you would be modulating like by 6 pixels, 10 pixels. So that would mean that you have an order of 6 or 10 times less resolution when you put it all together, but you would have the polarization in a single exposure, which for transients can be an extremely exciting idea. So as for operations, now I'll move on to how it is going to work at the telescope. This is an instrument that is thought to be very efficient, not only in observations, but also in calibrations. So this is very fast instrument with very short dead times, and this means that you can do things very quickly. For calibrations, we have very few modes. We have imaging and spectroscopy. You don't have to calibrate each filter one at a time. You calibrate all the filters simultaneously. As for so you can do all the flats and all the bands at the same time. The same for spectral photometric standards. You just adapt the exposure times independently to each of the arms, and you get a good exposure in each of the arms at the same time. So in a very short part of the twilight, you're going to be able to have all your flats and all your standards observed. Also, one thing to take into account is that many times when we observe with very broad wavelength coverage instruments, and here I've been using, for example, X-Shooter a lot, we have sometimes the problem of making all the arms match properly in spectral photometric calibration, because you can base your flux, you can offset your flux calibration to some photometric observation obtained with the acquisition, for example. In this case, we're going to have 8 different bands in acquisition. So you can correct your flux calibration to all the 8 bands that you obtain in the acquisition. So you can have a much stronger, much more solid spectrophotometric calibration in the instrument. In the science operations, you're going to be able to acquire in any band. So you're going to basically not need anymore to do blind offsets when you're observing an object that's very red or that you only see in the infrared, for example, that we have to do in other instruments. The astronomer at the telescope is going to have a real time SCD basically in front of his eyes. It's just going to see the shape of the spectrum. So for visiting time or for an experienced support astronomer, you're going to know what you're seeing already there. It's going to be, I mean, to me, it would be very exciting to be able to know what the object looks like for a transient. And as I said, this is the instrument that's more prepared, I think, to detect the highest redshift gamma ray burst and obtain spectroscopy event. One thing that we are exploring is the implementation in Gemini of a rapid response mode for science cases like gamma ray bursts or other science cases where you really want to go within a few minutes to the target. And this I'm going to discuss in a minute. We're also thinking of having an automatic target acquisition for these transient studies. So when we get an alert from a satellite or when we get an alert from LSST, we're going to have a position. So the idea is to have the possibility of the instrument running some software that will identify that transient within the error box that has been provided and acquire the object automatically to save time in operations. As for the rapid response mode, as I said, gamma ray burst is one of the main users of this kind of mode. This is basically when you're observing a target and a very high priority alert arrives that requires this kind of mode. The observations are going to be interrupted, and the telescope's going to immediately move to the other target and start observing. Of course, this is only going to be done with high priority targets where the scientific output is going to be important. This would allow to be on target within a period of around 5 minutes, 5-10 minutes, taking into account the movement of the telescope, the interruption of the observations, and the delivery of an active optics corrected image at the instrument. And finally, I'm going to just give you some examples of observations so you can have an idea of how we would look to be working with OCTOCAM sometime in mid-2022 when everybody's going to be able to use this thing, hopefully. So as you see here, you would have your 8 bands. You'll be able to do different exposures at the same time. You would have your object. You can just decide to get an image in a single band, or you can have an idea in color of what the object looks like. You can select your slit. You can put how you like. At some point of your observation where you're observing your favorite galaxy, you might have one of these alerts coming from Swift, from LSST, someone. And for example, this is going to be an example of a gamma ray burst observation where suddenly you get an alert. Your telescope points directly to a field. If you look at the field here, this is what we would have in a normal acquisition of a normal instrument that's like in the visible. You would see nothing in the field of view. But if you look in the different arms, you can see that although in the visible there's nothing, you can have something in the infrared arms that is more significant. So you can select to get the image in the infrared bands. Again, this would be done automatically by our source detection software. And you can see that there is actually some very prominent source in the infrared that's not seen in the visible. This, if I'm at the telescope, would already get me excited. So you will put the slit on your object and start spectroscopy. You go to the spectroscopic mode and you get your quick view reduction of the data. And you can see your spectrum coming up here on the H and the K band. And this is, I'm just saying, a realistic observation with the magnitude fluxes of a luminosity of a real object that has been scaled. This would be 300-second exposure. And this is what we would look like if this thing really existed. And so it would be very easy. Within a few minutes, we'll be able to detect this Lyman alpha dropout and detect this gamma ray burst and get a very nice spectrum within 300 seconds at a redshift of 11.5. That's one of my scientific goals to do with this instrument. Okay, and this is basically all I'm telling today. I leave you here with some of the specifications of the instrument. Let you start thinking of science cases that would interest you. If you have any scientific or technical comments, I'll be extremely happy to hear. We're still designing this thing. So if you have very good ideas or things that you would like to do with it, please come to me or ask me now. And we'd like to hear opinions and comments. Thank you very much.